Hello. Today I will be discussing groundwater flow modelling in the context of climate change and saltwater intrusion. Groundwater is a vital resource, supplying fresh water to billions of people, as well as supporting agriculture and industry. However, climate change poses significant threats to coastal aquifers, making it crucial to understand and predict these changes using groundwater models. In this presentation, I will compare three research papers that focus on groundwater flow modelling to assess the impacts of climate change and saltwater intrusion. By examining the methodologies, key findings, and limitations, I will highlight how these models enhance our understanding of this challenge. As mentioned, one arising challenge is saltwater intrusion. In coastal areas where groundwater meets saline groundwater, due to the saltwater being denser than freshwater, it intrudes into the aquifers, forming a saline wedge below the freshwater. This boundary is not fixed and shows seasonal variations along with tidal fluctuations, meaning the interface of mixed salinity can shift depending on conditions. Saltwater intrusion occurs when saline groundwater replaces fresh groundwater, a natural process which is influenced by human activities. It becomes problematic as saltwater reaches freshwater sources like wells. Around 40% of the global population lives within 100 kilometres of coastlines, relying on pumped groundwater for drinking. In densely populated areas, excessive water demand can lead to overdrawing, increasing salinity and making the water undrinkable. This is highlighted by the figure showing a typical well on the left and overdrawing on the right. Climate change is expected to worsen saltwater intrusion due to rising sea levels, extreme weather, coastal erosion, shifting rainfall patterns, and higher temperatures. Combined with growing freshwater demand, these factors heighten the risk of groundwater contamination. Now moving on to the research papers, I will briefly introduce each paper and highlight the main objectives of the modelling. The first paper by Van T et al. Aimed to assess the impact of groundwater extraction and climate change on groundwater depletion in the upper aquifers of the Tra Vinh province. More specifically, the study aimed to construct groundwater flow and saltwater transport models to analyse the importance of groundwater abstraction versus climate change. Secondly, it analysed the importance of salinisation from inland saltwater versus modern seawater intrusion in the area. In addition, the study looks at adaptation options for controlling groundwater depletion and saltwater intrusion. The modelling aims to simulate reductions of abstraction and increase in managed aquifer recharge. The findings from the modelling studies provide guidelines for sustainable groundwater resources development in the province. The second paper by Rasmussen et al. Focused on the island of Falster in the western Baltic Sea, with the aim of exploring the impact of climate change, including saltwater intrusion and changed groundwater recharge on a coastal aquifer, which is specifically influenced by drainage canals. The main goal is to determine the key drivers of saltwater intrusion and whether rising sea levels, shifts in recharge, or changes in drainage canal water levels have the most significant effect. To analyse this, the researchers used a coupled groundwater flow and transport model to simulate past, present, and future freshwater seawater distributions. They also examined how long it takes for climate-driven changes to affect groundwater quality, and whether water supply wells may need to be relocated due to salinisation risks. Lastly, Romanazzi et al. Focused on a large karstic coastal aquifer in southern Italy. This aquifer is the region's sole source of high-quality freshwater, but it's under serious threat from overexploitation, seawater intrusion, and climate change. To assess these risks, the study simulates groundwater flow and salinity changes from 1930 to 2060. By analysing different climate and human impact scenarios, the model helps us understand how factors like sea level rise, shifting rainfall patterns, and increased groundwater use affect water availability. Moving on to the groundwater flow models, before the final simulations, conceptual models need to be constructed. Conceptual models are simplified representations of groundwater systems, summarising the current understanding of the geological properties. This model acts as a hypothesis of how groundwater moves through a specific area, helping to guide further investigation and numerical modelling. The next slides will cover the conceptual models created in each study. Van T et al. Created a conceptual hydrological model using the groundwater modelling software, often called GMS. Conceptual model coverages were created using GIS utilities to represent physical structures, parameters, stresses, and boundary conditions of the aquifer systems. The model was designed to capture the spatial complexity of the multi-layered coastal aquifer system, where layered-based conceptualization allowed for an in-depth analysis of abstraction impacts, climate change scenarios, and potential mitigation strategies. Unlike the other studies, the research by Rasmussen et al. Did not explicitly construct a new conceptual model, but rather refined an existing hydrostratigraphic framework based on the DK model, which consists of 8 alternating quaternary clay, till, and sand layers overlaying a Cretaceous chalk aquifer. The chalk formation was further divided into 8 layers to differentiate between zones dominated by advection-driven solute transfer in the upper layers and diffusion-dominated transfer in the deeper layers. In the Romanazzi et al. Study, the conceptual model was developed to represent the Salento-karstic coastal aquifer in southern Italy. The aquifer in this study is very large and complex due to its karstic nature, and therefore can be considered as an equivalent porous continuous medium, allowing the complex system to be simplified. This method treats the fractured and cavernous limestone as a homogeneous porous medium and has been shown to be very effective at modelling at a regional scale. It's worth noting that the conceptual model approach is based on the research objectives and data available. Most importantly, they reflect the needs and challenges of each study area. For example, Vanti et al. And Rasmussen et al. Both emphasise geological complexity. However, Vanti constructed a conceptual model from scratch, where Rasmussen refined an existing one. Both Vanti et al. And Rasmussen et al. Employed highly detailed models to capture the complex hydrogeological processes within their study areas. In contrast, Romanazzi et al. Prioritised computational efficiency due to the larger study area, where the chosen method provided a less detailed but more scalable representation of the aquifer. Comparing each of the study's modelling methods, all 3 studies used ModFlow for groundwater flow simulation and CWAT for density-dependent transfer modelling, which is crucial when considering saltwater intrusion. The combination allows a realistic assessment of coastal groundwater dynamics. Regarding the grid geometry, all 3 utilise layered 3D structured grids. This suits both ModFlow and CWAT, which use a finite difference method which typically works best with a structured grid as opposed to an unstructured mesh. Each study uses a different grid geometry dependent on the modelling objectives set out. Rasmussen et al. Uses the smallest grid size of 50 by 50 metres and 32 layers. This high resolution allowed for the detailed tracking of solute transport and the sharp saltwater-freshwater interface, making the most precise model of the 3. The finer grid was necessary to capture the small-scale effects of drainage canals and sea level rise in groundwater salinity, preventing oversimplification. Romanazzi et al. Has the largest grid size, where each cell represents 0.48 km squared. This was primarily due to the large study area, where a higher resolution would cost more and require greater computational power. Along with this, karst aquifers can't be fully represented in ModFlow, and therefore a coarser grid was sufficient because the fine-scale heterogeneity of karst features would not be captured accurately. Vanti et al. Strikes a balance between the 2 resolutions with a grid size of 500 by 500 metres, balancing local and regional scale detail, whilst having enough detail to track coded depression effects concerned with pumping groundwater. Vanti et al. Derived their hydraulic parameters from pumping test data, professional reports, and existing literature. This method provided reasonable estimates for hydraulic conductivity and storage coefficients, ensuring that the model reflected measured field conditions. In contrast, Rasmussen et al. Used a more detailed and data-driven approach to assign hydraulic properties. They utilised the hydrogeologic unit flow package in ModFlow, which allows for layer-specific hydraulic properties to be assigned based on field data. This included values derived from borehole logs, geophysical surveys, and direct hydraulic head observations. Romanazzi et al. Took a simplified approach, using interpolated hydraulic conductivity and storage values from previous regional studies. Since their study treated the karst aquifer as a homogeneous medium, fine-scale variability was not explicitly modelled. Instead of assigning layer-specific field-based parameters, they applied generalised values suitable for large-scale groundwater assessments. For calibration, Vanti et al. Used the trial and error calibration with RMSE assessment from 13 observation wells to adjust groundwater levels. However, due to the limited salinity data, CWAT calibration for saltwater intrusion was not fully achieved, and results were instead compared to total dissolved solids distribution. Rasmussen et al. Used parameter estimation software for automated calibration, ensuring high precision. The model was validated against hydraulic head data, geochemical measurements, and airborne geophysics. The model demonstrated a high degree of accuracy, with a low prediction error and strong correlation between observed and simulated results. This level of calibration was essential due to the study's focus on the detailed solute transfer and density-driven flow modelling. Romanazzi et al. Also used PEST, but applied it at a regional scale, adjusting hydraulic conductivity recharge and storage properties. Limitations are expected in groundwater flow modelling, as no model can capture every detail perfectly, and a balance between simplification and high detail should be met to ensure the model is reliable and accurate. However, it is important to be aware of the limitations of the assumptions made and what uncertainties they may introduce. Initially looking at the study by Van T et al., one limitation is the assumptions made for the boundary conditions, where lack of data meant the coastline was the general head boundary, as it's unknown how far the aquifers could extend beneath the seafloor. Along with this, layers 6 to 13 of the model were assumed to be no-flow boundaries, as there was no data stating what the nature of the boundary was, which may not capture tidal fluctuations or seasonal variability. Along with this, seawater calibration had no direct salinity data and assumed that the total dissolved solids adequately represents saltwater intrusion, which could possibly cause misinterpretations of saltwater intrusion. Furthermore, this paper only considers climate change effect on future precipitation patterns and does not simulate results for increased temperatures or sea level rise. Both Van T et al. And Rasmussen et al. Used MT3DMS for solute transport modelling alongside CWAT, allowing them to independently model advection, dispersion, and chemical reactions. However, Rasmussen et al. Had access to a more diverse dataset for solute transport validation, incorporating data such as chloride concentrations, total dissolved solids, and groundwater age tracers. This provided a more refined validation of saltwater intrusion processes compared to Van T et al., which lacked direct salinity measurements. Rasmussen models additional validation data likely improved the confidence of saltwater transport predictions, making it more robust in this aspect. The main uncertainties in the Rasmussen paper was that the geological units were assumed to be homogeneous, which is not the case, and the degree of heterogeneity cannot be quantified based on its available data. This oversimplification of the chalk aquifer may cause the model to underestimate preferential flow paths, leading to a less accurate model. Secondly, data on groundwater abstraction is only available of waterworks rather than individual wells, leading to evenly distributed abstraction estimates, and because actual well abstractions rates can vary, this assumption introduces significant uncertainty in local groundwater head predictions, potentially affecting model accuracy in areas of high pumping activity. Lastly, the hydraulic head observations used for calibration were collected over more than 10 years, meaning some were recorded during wet winter months and others during dry summer seasons, meaning the model may not fully consider seasonal fluctuation. Due to the larger size of the study area in Romanazzi et al.'s research, it is subject to the large contributors of uncertainty. However, for the purpose of the study, these assumptions don't necessarily cause an issue, but introduce uncertainties nonetheless. The main criticism is the treatment of the karst aquifer as homogeneous porous medium, which neglects preferential flow, which can mean the model predicts saltwater intrusion at a slower rate. Along with this, unlike the other two papers, mitigation strategies are less explored, with adaptations being acknowledged, but their recommendations being qualitative. Finally, moving on to the synthesis of learning. Each paper takes a unique approach to modelling based on its objectives and the type of coastal aquifer, but collectively they provide a more comprehensive understanding of saltwater intrusion, by ultimately providing a conclusion on the drivers and impacts of saltwater intrusion under different scenarios. Importantly, considering the papers together allows for analysis of assumptions and justifications, which means the paper's strengths and weaknesses are more evident. One key takeaway is the scale and resolution for saltwater intrusion modelling. Romanazzi et al. Considered a large area and provide broad saltwater intrusion trends driven by climate change, but they lack detail on local geology and small-scale effects. In contrast, Rasmussen and Van T et al. Have a greater resolution in a smaller study area, helping show finer details such as the impact of canal management or more precise movements of solutes. But these models can miss out on the broader impacts of saltwater intrusion in the region. A second important takeaway is the results the studies yield. All three of these papers deal with the impacts of climate change and saltwater intrusion, but Rasmussen and Van T et al. Both found that human activities such as over-extraction and canal drainage can accelerate saltwater intrusion more than climate change alone, indicating the importance of considering both human and environmental impacts when modelling. Ultimately, the three studies have shown that there is not a model which can fully capture the true dynamics of saltwater intrusion by itself. Applying an integrated approach with the learnings of previous studies to assess the most effective solutions will provide more well-rounded simulations where we can better predict saltwater intrusion risks, assess mitigation effectiveness, and plan for future changes. This concludes my presentation. So thank you very much for listening, and please see my references in the next slide.